Okay, so we're going to jump into cycle 2. We're going to look at the derivative of both sine and cos in this lesson, and we're going to introduce a wildly important rule, a rule that we will use literally in every lesson from here on out, which is the chain rule. So here is the graph of sine. We're going to use this to kind of sketch what we think the derivative of sine should look like. I see horizontal tangent there, so slope should be 0. Horizontal tangent there, slope should be 0. Same with there, same with there. Now, at the origin here, we've got some sort of positive slope, so I don't know exactly how high it goes. I don't know if that's a slope of 1 or if it's a slope of 2 or whatever. So I'm going to put it at 1. I've drawn this to, so I asked Desmos to make the scales the same there, so that looks to me like a 45-degree angle, so that looks like the line y equals x. So I'm going to guess that's 1. And similarly, I'll guess that there is -1. And here again, +1. And I'll just chase that along, so that looks like a -1, +0, and then that looks like a +1 there. I don't know if I connect those dots up. And ask myself what that looks like. It looks like it might be cosine. And again, I don't know if that's exact, like I'm guessing that this is a slope of 1, but if this is, a slope of 2, then maybe it's, 2 times cosine. But it's definitely it looks very much like cosine to me. So it could be cosine, it could be 2 cosine, it could be some stretch of cosine, but just looking at the picture, it looks like that. Similarly, if we do the graph of cosine below, if we sketch its derivative, okay, let's put on the points that we know for sure are 0. And again, let's look at these. So that looks like -1 to me again. It kind of looks like the 45 there. That looks like a slope of +1 through there. There, that's a slope. Positive, negative. So it looks something. Looks something like this. And unfortunately, that doesn't look exactly like sine, but it's definitely sine-like. It's basically, if we look at this graph, it's sine kind of flipped upside down. So that'd be like negative sine of x. And then again, that's a maybe. We're not exactly sure yet because we're kind of guessing that that's a -1, but it could be -2, and then it'd be -2 sine x. Okay, so it's again some sort of vertical stretch of sine, it looks like, and it's definitely a negative value in front, a reflection of sine as well. So that's our guesses. I'm going to actually prove the derivative of sine. We're going to use Desmos to help us out here. So we don't have a rule for trig graphs. We've got to go back to first principles. And right away, I'm kind of stuck, but I see sine of x plus h. I remember we had a formula for that in advanced function. Sine cos plus cos sine, I believe. My memorization from university is staying with me. Sine cos plus cos sine. So we'll fill that in. So sine of my a is going to be x. My b is going to be h. plus cos x sine h, and then minus sine of x all over h. Okay, that's different. I don't know if it's helpful or not, but there we go. That's something anyway. And then what I'm going to do is I'm going to notice this term has a sine x and this term has a sine x. And so what I'm going to do is I'm going to group those two terms together and factor out the sine. So sine of x times cos of h. So that's that first term minus 1. There's my second term. So that's these two terms with the sine factored out. And I still have completely separately over here the cos of x times the sine of h. Can't do much with that. And then there. And what that's done for me is it's kind of split these two pieces into something with just an x here, just sine x there, and then in brackets no x's, just h. And then this term over here, cos of just x, sine of h. Okay, so it's sort of split each piece into something with x's and something with h's. And what I'm going to do now is I'm going to take these two things and break them into two separate fractions. So I'm going to basically have this and that. And then I'm going to go even further. We have this thing, if you have two things in a limit, you can take the limit of each thing separately. And then I'm going to go even further. And sine of x doesn't care if h goes to 0. So if h goes to 0, sine of x stays as sine of x. If h goes to 0, cos of x stays as cos of x. So all that, I can kind of factor out the sine of x because I know that it doesn't care about the limit. And I can figure out the cos of x because I know it doesn't care if h goes to 0. And just focus in on these different things. All right, so if I look at these, so basically all I've done is I've brought this limit, split this overall limit into two, and I factored out the stuff that is kind of constant in terms of the limit. Sine of x doesn't care if h goes to 0, cos of x doesn't care if h goes to 0, so I've just kind of separated that out from the limit. So I'm going to get the answer of this limit and multiply it by the sine of x, the answer of this limit, multiply it by the cos of x. And so what's happening here, so this is our derivative of sine that we're starting with. The derivative of sine, this limit here should be, if it exists, should be a number because it's the limit as h goes to 0 and everything inside of it is h's. So it should be some number times sine of x and some number times cos of x. And if we look back at our picture, our guess was that the derivative was in fact cos. So our guess is that this number here equals 0, and our guess is this number here equals 1, so that we get just cos of x at the end of the day. And so if you try plugging in 0, you get cos of 0, which is 1. 1 minus 1 is 0. H is 0. So this is a 0 over 0 limit. And same thing here. This is a 0 over 0 limit. And what happens basically is there's more work to do. That's what 0 over 0 means, is there's more work to do. And the work to do here is basically a lot of trig identities that you haven't seen before. So I could sort of talk on this lesson for another 20 minutes throwing out random trig identities. But basically what we're going to do, I call this a Desmos supported proof. So I'm going to start with the cos limit. So sorry, this limit, sine h over h as h goes to 0. We'll jump over to Desmos, sine x, and just x. So what we're doing is the limit as sine of x, limit as h goes to 0 of sine of h over h. Now I can't punch h's into Desmos, you have to use x's, but basically what we're looking at is we're looking at the red graph divided by the blue graph as x goes to 0. And as you see, as x goes to 0, those two graphs are lying directly on top of each other. So as x goes to 0, those two graphs are basically the same number. And so what I should get if I divide basically the same number by itself is I should get 1. And so what I'm going to do is kind of show you that here. If you do sine of x over x or 0, yes, in fact, that graph is approaching 1 as x goes to 0. So that's our first limit. So it's cos of x times 1. Same sort of idea, we're going to look at this other limit, cos. So it's cos of x minus 1 and x. These are the two things we're dividing now as h goes to 0. And as we see, so we're doing green graph here divided by purple graph. As you can see, the cos thing, cos x minus 1, is basically already 0. It's basically already 0 when the purple graph, relatively speaking, is way far away from 0 still. The purple graph's at 0.01. The green graph's at 0.005, like 2 more zeros in there. 0.00005 when this one's at 0.001. So, you know, it's way smaller than the purple graph is what I want to see. They're both small, but the green graph way smaller than the purple graph. So I have something that's basically 0 divided by, relatively speaking, something that's basically not 0. So when you take 0 and divide by not 0, you should get the answer of 0. And so I'll look at these two things put together. I should have done this. That graph there, cos of x, I'm way zoomed in here. There it is. That graph does, in fact, sort of go to 0 as x goes to 0. So we get sine of x times 0 plus cos of x times 1. I'll say thanks, Desmos, for the help on those limits. And so that boils down to just cos of x. And so what we've proved is if y is sine of x, then yes, in fact, y primed is cos of x. Similarly, I could go through something similarly and work with the cos of x, use the cos of a plus b formula, and you will prove that it is, in fact, the negative of sine of x. I'm not going to go through those steps because actually if we learn what the chain rule is, then we can actually get the derivative of cos without first principles. So I'm going to go on to the next part of the lesson, and we can prove the derivative of cos is negative sine later. But this is kind of, you know, a proof that we had to use the computer to help out, but it is a proof that the derivative of sine is in fact cos. So that's kind of neat. Not anything that I'd ever ask you to reproduce on a test, but I always find it important to understand where this stuff comes from. So I'm gonna shrink all that stuff down. Fill in the stuff I actually did that so that I have room for my chain rule. So the idea here is what the chain rule is for is when you have a function inside of another function. So the sine of 5x plus 4. And just like I usually like to prove the rules that I show you, but with the chain rule, the proof of the chain rule involves like very complicated, very advanced, like 3rd year, 4th year university math. So I'm not going to be able to show you that. You're welcome to Google proof of the chain rule on your free time and look at how neat it looks, but not something I'm going to do. I'm just going to show you how it works. So basically, you have a function inside of a function, okay? So how this is going to work. So what the chain rule says is when you have a function inside of a function, the derivative is, what you do is you take the derivative of the most outside function. So the most outside function is sine. The derivative of sine is cos. And you leave that inside function plugged in. So you leave the inside function there. So derivative of the outside, leave the inside function there, and then completely separately multiply by the derivative of the inside function. So the derivative of the inside function here is 5. And that's the chain rule. So you do derivative of the outside, leave the inside there, and then multiply by the derivative of the inside. So the derivative of 5x plus 4. And this explains this example that we could do from first principles, but we didn't really have an explanation of why this works. So I'd rewrite that as this. I've just rewritten, don't lose communication marks, that's still f of x. What my chain rule says to do is do the derivative of the outside. So this is something to the half. Derivative of x to the half is 1/2 x to the minus a half, subtracting 1 from a half. What the chain rule says is just treat the inside like an x, and then separately do the derivative of the inside. And if I clean that up, if I wanted to, that 5 would be in the numerator, the 2 would be in the denominator, 5x plus 4. So that's one that we couldn't explain before. It's because we didn't know this chain rule yet. So you can pause the video here. You can try and fill in the rest, and then I will go through them when you've unpaused. So I'm going to keep going, but you pause now. See if you can use this chain rule to make these happen. So this one here, the derivative of the outside, the derivative of cos is negative sine. Leave the inside function plugged in, and then completely separately multiply by the derivative of the inside. There we go. Next one here. Oh, again, don't lose communication marks, Mr. Clement. Rewrite the third root as to the power of 1/3, and then take the derivative. The 1/3 comes down. You get x squared plus 3x plus 2. That stays put. We're going to end up with negative 2/3 when you subtract 3/3 from 1/3, and then completely separately multiply by the derivative of the inside. There we have it. This next one looks crazy. It is a bit crazy. It's basically a chain rule inside of a chain rule. So f prime of x is, do the derivative of the outside. Derivative of sine is cos. Leave the inside function there. So the inside function is cos of 4x squared plus 2. Now the chain rule says multiply by the derivative of what's inside. So what's inside is cos of 4x squared plus 2. Okay. Derivative of cos is minus sine. Leave its inside function there. And then the chain rule says, once again, multiply the derivative of what's inside. So in order to do the derivative of this piece, this inside piece, I need the chain rule again. It says do the derivative of this. And I've hit a derivative that I no longer need the chain rule for. The derivative of that inside is just 8x. We know that one already. So I think we're done there. This one here, I have 5x plus 3 as my inside. I have x to the power of 9 kind of as my outside function. I've got x to the power of 9, but instead of x, I've got 5x plus 3. So our normal rule applies. The 9 comes down, changes to an 8. This chain rule says multiply or leave the inside function there, and then separately multiply by the derivative of the inside, which is just 5. Here's my last trick. You have to remember what this notation means. So sine squared of 5x minus 2. What that means, it's short form for this, the sine of 5x minus 2 squared. So we put the squared on the inside so that you don't need these extra set of brackets, because if those brackets weren't there, it would be kind of ambiguous. Is the whole thing squared, or is just the 5x minus 2 squared? So we need these extra brackets if we're going to write it that way. I encourage you to rewrite it that way because you're less likely to make a mistake here. The 2 is going to drop down in front. The inside function is going to stay there. The 2 is going to become a 1. You don't have to write that, but I did. Now we're going to do the derivative of the inside. Derivative of the inside is another chain rule. Derivative of sine, though, is cos. Leave its inside function there. Completely separately. Multiply by the derivative of the inside. So there we have it. And again, all of these can be simplified, but usually I'm just doing first line only. So you can simplify further if you needed to do anything with these derivatives. We'd have to simplify them a bit more like I did with this one here. But in general, if I'm just asking for the derivative of something complicated like this, I'd rather actually mark it when it looks like this. It's easier for me to see that you've got all the parts. So we'll leave it like that. To write that as a formula, if you have f of g of x, it says you do the derivative of f, you leave g of x inside, and then you do the derivative of g of x separately multiplied at the end. So that's the formal way to write up the formula. Often people find it easier just to kind of explain it in words than actually use that formula, but if you want to see the formula, that's what it would look like. Oh, and I promised the derivative of cos. So how that one works is to turn cos into sine, because we now know the derivative of sine in theory, that we proved that the derivative of sine is cos. Let me just get this right. So derivative of cos. So here's sine of x. So to turn sine into cos, you have to shift it backwards by pi by 2. Did I get that right? No, I went the wrong way, didn't I? And I think it wants a little pi. Come on. Yeah, so there we go. So shift it left by pi by 2. Now the two graphs are the same. So you rewrite cos as sine of x plus pi by 2. Chain rule, derivative of sine is cos. Leave the inside function there. Multiply by the derivative of the inside is that. So there's our derivative of cos. It's the cos of x plus pi by 2. There we go, it worked that time. Which is that graph there, which if we rewrite is in fact sine flipped upside down. So there's kind of your proof that the derivative of cos is negative sine using the chain rule. I don't know why it's not showing up on top, but it's there. So that's kind of the proof of that. So you can make some notes. What's the derivative of sine? What's the derivative of cos? Both of those things should go on your formula sheet. When you see sine, you can write down its derivative right away. You don't have to do first principles. Its derivative is cos. When you see cos, you can write down its derivative right away. It's minus sine. What is the chain rule? How does it work? So you can write some summaries of how that works. And then you can take a stab at this one, and I'll take it up when I see you in class. And then you can work on this practice work in class as well. I'm not done talking. I'm back. One thing I meant to say. Where I went into Desmos and said, well, this is 0 and this is 1, I said to formally prove these two limits, I'd have to use a bunch of trig identities. The fun thing is, those trig identities that they use only work when x is in radians. So this derivative, why radians are so important, the derivative of sine is cos only if, I don't know what's going on here, only if x is in radians. So that's something that's kind of really important, is it only works if x is in radians. So these two derivative formulas only work in radians. That's why mathematicians work in radians.